Welcome to Module 8. In Module 8, we're going to take a look at sniffing. For sniffing, we have 4 different areas that we want to discover. So let's have a look at these 4 areas. We're going to start with a little bit of a summarization of sniffing concepts. We're going to move from there into different sniffing techniques, and then we're going to use different sniffing tools, and then we're going to give an overview of some of the sniffing countermeasures. Let's get started with a look at sniffing concepts. What is sniffing? Sniffing just might be more than you thought. So a lot of times when people think of sniffing, what they're looking at is using a tool, for instance, like Wireshark, to gather information passively from a wireless network or a wired network. It's more than that. So let's talk about sniffing. First of all, with packet sniffing, there are a couple of requirements. Number one, you have to have a network interface card that is in promiscuous mode. In order to talk about what that means, let's talk about what a network interface card does. So what it does is it is connected into a network. It could be wireless network, or it could be a wired network. And it looks at frames, OSI model, looking at layer 2. And if there is a MAC address, that the to address is the same as the MAC address on the NIC, then it'll process that frame. However, if the MAC address does not match the MAC address on that NIC, on that network interface card, well, then it will drop that frame. And there are other circumstances where it'll process the frame. One of those would be for multicast frames, and the other would be for broadcast frames. However, on a unicast frame, if it's not bound and addressed for that network interface card, then it won't be able to read it. So that is why there's another type of sniffing that we'll talk about, which is active sniffing. So anyway, that's what we're doing. We have a network interface card. It's running in promiscuous mode. It reads every MAC address, irrespective of whether it's addressed to it or not, because it doesn't care. It's in promiscuous mode. And because of that, we can gather information through sniffing. So I was mentioning a little bit earlier passive sniffing. Passive sniffing is when we are just listening to what's happening on the network, like with Wireshark. Whereas active sniffing is when we are sending data in to the network to elicit a response. And then with that, we can get even more information that we would normally not have been able to see before. So MAC flooding, DNS poisoning, ARP poisoning, DHCP attacks, switchboard stealing, and spoofing attacks are all part of active sniffing. And so as an attacker, you're going to be probably using passive sniffing to discover items about the network. But when you really want to get deeper, you'll use active sniffing. All right, so let's have a look at the OSI model. I've been mentioning it before. You really should know the OSI model. It probably before you even got into this class. But if you haven't learned the OSI model, that's something that you can add to your basket of knowledge. And so what we have is the physical layer. That's layer 1. Layer 2 is the data link layer. Layer 3 is the network layer, transport, session, presentation, application. So if you want to memorize it, I bet you have it memorized, don't you? Do you remember the mnemonic for memorizing the OSI model? Let's see. Please do not throw sausage pizza away, or all people seem to need data processing. So I like the all people seem to need data processing better. But another thing I want to tell you about, and you'll hear my terminology throughout this class reflect this for the most part, and that is at the data link layer, we call that a frame, that bundle of ones and zeros. At the network layer, we call that a packet. And at the transport layer, we call that a segment. So down at the physical layer, it's just bits. So either way, what happens is if you look at a switch, like a Cisco switch or something like that, and you have a device like a computer that has a network interface card, and you plug the computer into the network interface card, and then you take a cable and plug that into the switch, that's the physical layer. But that network interface card, when those ones and zeros form into a frame, you're at the data link layer. So from the data link layer all the way up is where we're dealing with sniffing. So all the way up to the application layer. So you have a switch, and if you look at this switch that we see on the screen, we have all these hosts that are connected to the ports of the switch. So if you look at the far left host, I'm going to go ahead and draw on the board here. I think this is a good time to do that. So when we look at the far left host on the left side of this, what we're looking at is port 1. So I'm going to put a number 1 there. And then let's look at port 4. So port 1 and 4. So if I have a host that's connected to port 1 and it sends communication over to the host on port 4, that communication is switched. It doesn't touch any of the other ports at all. So if I am the attacker and I'm plugged into port 3, I will not see any of that traffic at all. So what I can do as somebody who has some control over that switch is I can create what's called a span port. And I can tell it, hey, give me ports 1, 2, 3, 4. I can do port 5, 6. I can get them all. And I can say copy all of that information to this span port. And so let me see if I can draw that better. So we copy that information to the span port. So it all goes over there. And then I can have my laptop, or I can have another device, and I can collect all the information from all of the ports on that span port. So that's what a span port is all about. It's great also if you're connecting an IDS or some other type of device that needs all of that information. Right on. So that is the span port, and you really need to have administrative access to the switch before you can make use of a span port. On different switches, a lot of the enterprise switches have the same capability, but it's not always called a span port, but it's the exact same technology. All right, let's have a look at objective number 2, and we're going to demonstrate some different sniffing techniques. And so the first thing we need to look at is what is going on with a switch. In particular, what we're looking at is the MAC table. And as you see on the slide, it's called the CAM table. And let me go grab the pen. I think I don't have a pen here. All right. So we have the CAM table, and that's actually a content addressable memory. It's a type of memory. What is it that's stored in that memory that's over here, this MAC table? What is in this MAC table? We have MAC addresses over here, :hex, and the main secondary thing that we have is ports. These are switch ports, physical switch ports that we have devices plugged into. Now, there's other like aging and learning and type and VLAN, etc. But the main thing we're concerned about is the switch port. So that MAC address has an OUI and has a network interface specific part of the MAC address. We can make it unicast and broadcast. There's all kinds of stuff you could look at with the MAC address. But what I want to emphasize is this. On a regular work group switch, commonly, it can hold 8,192 entries. So this table, 8,192 entries. If you have a 48-port switch, that's quite a lot for a 48-port switch. For larger switches, you can have over 131,000. And for the core switches, you can have up to 288,000 entries. It's actually north of both of those. So you can have quite a lot of entries in this switch. Now, most switches that you're going to be hacking are going to be workgroup switches that are set to 8,192 unless the network engineer decided to set it up to 131,000. So that MAC table is never going to get full from normal operations. Because if you have an entry in the table that hasn't been used in a long time, it's going to age out. And then other entries over time. I mean, how often are people plugging in new devices into that switch? So you need to know these dynamics, but there's more than that that you need to be aware of. You also need to be aware of how switches learn. So what happens over here is we have a computer, and it has a MAC address of A. That's a pretty short MAC address, but that's the representation. And in the MAC table, we see that we have A that's mapped to port 1 on the switch. Well, this computer is looking for a computer, another computer on the network. And what it's saying is, hey, I am IP address, maybe you would call this 1.1.1.1. Are you 1.1.1.2? So it sends out a broadcast, and every port on the switch sends that broadcast out. Now, the computer that it's ARPing for is B, and the switch has not yet learned that it's connected to that port. So it floods, that's what the actual term is. It's called a flood. It floods that information out all of its ports, and then all the other computers on the network drop that frame. But MAC-C, that is IP address 1.1.1.2, will say, yes, that's me, and it will send back a response into the switch, and the switch will now learn that a MAC address ending in B is on port 2, and then the MAC table will have that mapping in it. So the next time any of these computers want to communicate with each other, there will be no need for flooding. It will just switch the frame from one port to the appropriate port. So that's what's happening in the background. Now, once all 48 ports have devices on them, then there's no need for other MAC addresses, at least not right now. And the switch is stable, 48 MAC addresses roughly, and so that's far less than 8,192 that would be available to put onto that switch. But what happens if we fill it up? We use all 8,192 slots. Well then, you're in big trouble because your switch will act like a hub. Let's talk about what a hub is. So, because a lot of you have come into the networking world after the age of hubs. So this is a poorly drawn hub here. So I'll even label it hub. And so let's say I have devices connected to all of these ports. And what a hub is essentially like what we call a multi-port repeater. So if this device sends in data into port 4, then it just gets reflected out all the ports. It doesn't care what it is. So if this device over here sends data into port 1, it just gets reflected out of all the ports, which is great if you are a hacker. Because if you are a hacker, all you have to do is plug into any port and you can see everything. So that's why you want to avoid your MAC table getting through. And that's why the network engineer might set that table limit to 131,000 rather than 8,192. But I tell you what, they can't stop you. You know why? Because you can use a tool like MACOV, which what it will do is out of the port that you specify, it will flood up to 131,000 entries. They're all fake entries per minute, filling up that MAC table, and now the switch will act like a hub, and I can be plugged into any port, and I can see all traffic from all 48 ports or however many ports there are on the switch. Isn't that cool? I like that. So we have the ability to get that information by using one simple command. There's more that you can do with a switch. Let me close that out, put this down here. There's a lot more you can do with a switch. You can steal ports. So normally there is the ARP process. ARP is an address resolution protocol. What it is it allows a device that is on the subnet, on that switch, to find other devices by saying, hey, I am this IP address. Are you that IP address? Give me your IP address and your MAC. Then the ARP table is filled in both devices, and then they can communicate with each other through the switch. But there's another type of ARP. It's not saying, hey, I am this, are you that? It's saying, hey, everybody, I want you to know, put this in your ARP tables. And it sends out information to everybody, and that's called gratuitous ARP. And so what you can do is you can use what are called forged gratuitous ARP frames. You send a huge amount to it, overwhelming the switch. So eventually you drift into using a separate port. You can actually steal a port using forged gratuitous ARP packets. Right on. So let's look at a few other things that you can do with switches. One of the things that you can do is defend against an attack. So what you want to do is take that 48 port switch, and let's say that in my office I have a desktop computer that's plugged into a port. Well, that desktop computer has a MAC address. And what I can tell the switch is say, hey, you know what, the MAC address that's plugged into port 3 right now, that is the only MAC address that can use port 3. So if an attacker snuck in at night and removed my laptop, unplugged it, and plugged in their laptop or their Raspberry Pi or whatever, guess what? It's going to not allow that to happen. So how do we do that type of defense? Well, all 48 ports need to have this. Let's go over here and have a look. This is port security. Now, I will tell you about port security that this is a little bit overkill in terms of Cisco. You can do this with about 3 commands. But this is actually for overkill. It's actually a really good one. You could actually copy this and adjust it to your switch. And then you paste it into each port. And you have a nice way to defend against attacks against that switch. And then for this, when the guy tries to steal a port, he won't be able to because only one MAC address is allowed on that port. There are other types of attacks that we can do. Another one is a DHCP starvation. DHCP, the Dynamic Host Configuration Protocol. What does it do? Well, it dynamically configures hosts with IP addresses. So what happens with DHCP is you have what's called the DHCP DORA. And DORA, let's have a look at DORA over here. And with DORA, we have these messages that are sent out. And the D in DORA, it's DORA. D for DHCP discover, right? So O for DHCP offer, R for DHCP request, and A for DHCP act. DORA. All right, so what happens is this computer sends out a DHCP discover. It's a broadcast, so it's like yelling on that network. Hello, hello, I'm looking for a DHCP server, right? And so every DHCP server on the entire network will send back a DHCP offer. Hey, I can be your DHCP server. I can be your DHCP server. The first one that arrives will get the DHCP request. All the rest will get what's called a NAC. No, I already have one, right? So we send out a DHCP request. Yeah, will you be my DHCP server? It's broadcast. It's like it's yelling. And then that DHCP server will send back an acknowledgement saying, yes, I'll be your DHCP server. And now they communicate unicast to each other. And now that device has a DHCP server. So let's look at what happens here with a DHCP starvation attack. And before I do that, I need to do a little erasing on this board so that we have the appropriate marks here. So with a DHCP starvation attack, what's going to happen is this hacker, this ne'er-do-well, or it could be me, I might be running it in a lab, is going to send up a whole bunch of illicit requests to the DHCP server, and you're going to fill up all the DHCP scopes. The scopes on the DHCP server are like the IP address ranges that you have for subnets or VLANs on the network. So we can starve it with tools like Eurocena. Eurocena is my favorite of the ones that are listed here, DHCP starvation. Metasploit has tools for DHCP starvation, and there are others. And then for DHCP rogue server attacks, what I'm going to do is, as the attacker, I can set up a DHCP server. It could be in my laptop. It could be in a Raspberry Pi. It could be an app that runs somewhere. And all it has to do is answer the request first. And then if it does that, what's going to happen is the attacker will be able to supply the IP address, the subnet, the default router, the DNS servers, and lease time, etc. And so the attacker can then use that to send requests to his or her own server. And that's a rogue DHCP server attack. All right, so the next thing we want to talk about is defending against DHCP starvation and defending against rogue DHCP server attacks. So let's have a look first over here. What we want to do is that setting that we saw before, enabling port security. We want to do that first. So these are some of the commands: switch port security, switch port security max 1. And I told you could do it with 3 commands. Then we do a restrict, and then they give you the rest of the address, sticky, and so on. So what happens now is it's only going to allow this user's MAC address to be used. That is the first defense. The next one is we want to enable DHCP snooping. And so we enable it, and that allows the switch to accept a DHCP transaction directed from a what? Trusted port. All right, so the first thing we're going to do is we're going to turn on DHCP snooping. This is a global command, which means it affects the entire switch. And then we're going to do an IP DHCP snooping VLAN, and we specify VLANs against which this command applies. And then we're going to do an IP DHCP snooping trust. So we're assuming that everything is perfect right now, and we trust those locations and those locations only. So if there is a DHCP server that's placed on the network and it's not one that's trusted, then the communication won't be allowed. All right, let's talk about another type of attack. This is probably one of the more important ones that an attacker will use to get information from other places on the network, and that is an ARP spoofing attack. So let's have a look at how that works. So the address resolution protocol, I was already describing it before, where it helps to line up an IP address with a MAC address. That information is cached in ARP cache on every device that makes use of ARP, which is every device you can imagine, just about. And so what it does with ARP, it resolves that IP address to a MAC address. So what's going to happen is this user right over here is going to say, hey, I need to connect to 10.1.1.1, but I don't have its MAC address. No communication is going to take place without that MAC address. So it sends in an ARP request to the switch, and the switch broadcasts that ARP request looking for that IP address. What should happen is that device should respond to the ARP request saying that I am 10.1.1.1 and here is my MAC address. But in this case, instead, a malicious actor responds. And now this device, user A, and every other device that has that ARP cache will send their information to the wrong device. And so you can collect information from multiple locations. So as an attacker, that makes it very nice because you can actually set up ARP spoofing. Well, we're going to do this in the lab, by the way. It's pretty fun. You set up ARP spoofing, and then you can collect information from all over the network without having to worry about the fact that you're on a switch, and the switch is only going to allow you to see frames that are bound for your network card's MAC address. So ARP spoofing is the way to go if you want to collect information from all over the network. So there are tools that we can use for ARP spoofing, and there are a lot of them, by the way. So if you look at the first tool that we have here, it's called ARP Spoof. Second one's Habu. Both of those are very good. I like ARP Spoof better than Habu, but they'll both do it for you. But the top two tools I want you to really know are the top two in the table on the right, which is BetterCap and EtterCap. And what I am going to point out in the lab is you want to keep track of the steps that we use for BetterCap and EtterCap. You need to know those for the exam. How do you defend against ARP poisoning? Well, let's have a look here at this slide. So to defend against ARP poisoning, what we're going to do is we're going to implement DAI. DAI is Dynamic ARP Inspection using the DHCP snooping binding table. And so see this little command SH? On a Cisco device, that means show. So show IP, which is the protocol, DHCP snooping binding. And so what it'll show you is what interface where the DHCP server is. And so if that is good, we check that. We want to make sure, as we see down here, that the MAC and the IP fields that are good, right? The ARP interface is bound correctly. The rest is going to be blocked. So that's the first thing we want to do is do IP DHCP snooping binding. And the rest of that, we have several other Cisco commands. And by the way, we're doing Cisco. And if you have switches from other organizations like HP or whatever, every one of them has their own language, and they're fairly similar in some cases. And other times they're a lot different. All you have to do is do a little search for what we're trying to accomplish, right? So in this case, dynamic ARP inspection. So let's look at the actual commands for a Cisco device. So IP DHCP snooping, we turn that on. And you see that switch where it says config in parentheses? That means we're in global config mode, so anything we type will affect the entire switch. And then we specify the VLAN. Right now, we're going to use a show command that's just going to list out what we have. And so we have it enabled, and it tells you the VLANs, etc., and it lists that information out. Another thing we want to list out is the snooping binding to make sure we know that DHCP snooping is turned on and that it's working. Once we have both of those set up, then we can go to the third step, which is to do IP ARP inspection VLAN 10. And now we are turning on dynamic ARP inspection. It's going to keep track of who's doing what in terms of ARP, and then we can do a show command or SH, IP ARP inspection, and it shows us what is happening. In fact, some of these show commands are dynamic, and you can watch it happening in real time and make sure that nobody is hacking ARP on your Cisco architecture. So what are some of the tools that we can use to detect when someone's trying to do ARP spoofing? Let's have a look at some of these tools. The first one that we're going to look at is CASPA Portable Network Analyzer. This is sort of like a fancier version of Wireshark. And of course, in the upper right-hand corner, we have Wireshark. We have NetProbe and many others. That what we're essentially doing is just watching the network to make sure that everything is normative on the network. All right, the next thing you want to look at then is duplicating MAC addresses. Sometimes you need a new MAC address. Let's talk about that network interface card again. So the network interface card has what's called a BIA, a burned in address, but it also has an advertised address. The burned in address cannot be changed. So whatever that is, you can't change it. However, you can advertise a completely different address and duplicate that address. So if you look at what we see here, we have a legit user. And the user says, my MAC address is AABE, all the way through FF. So what this guy does is he sniffs the network and, oh, hey, I want that MAC address. So he advertises his address as the same. And this could have a lot of different implications that we'll look at in many different ways as we get deeper into the class. One of the things that often people are unaware that is a possibility is this thing called IRDP. IRDP is a router discovery protocol. And what you can do with IRDP is very interesting because if you have IPv6, an IPv6 network, this is actually how it's supposed to work. But that was actually copied from this capability that exists in IPv4. And what this does is a router can say, hey, everybody, through multicast, right? Saying, hey, everybody, I want you to know that if you want to get out of the network, all you have to do is contact me and I'll give you a path out of the network. And so this device will also respond to that IRDP router and say, hey, thank you. I can't get out of the network. I'm going to use you as my router. However, the IRDP router is put up by the attacker, and now they can control the communication and where it goes. All right, now let's look at the idea of VLAN hopping. So when I have a switch, what happens is whatever port that I'm plugged into on the switch will have a VLAN assigned to it. And when it has the VLAN assigned to it, that is the only VLAN communication I can have. There are some special circumstances where you can have a phone and you have a computer plugged into through the phone, and we have two VLANs in that case. But that's a special circumstance. Normally, you're just in a single VLAN on a single port on the switch. But there are ways that you can hack your way into another VLAN. Let's look at a couple of different ways here. This is called VLAN hopping. And so the first one that we see on the left side, let me go ahead and grab a laser pointer. On the left-hand side, so what we see on the left-hand side is a rogue switch. So what this attacker did is they got a switch and they plugged in a trunk port, and they turned the port into a trunk port, and then they plugged the cable into this switch, which is probably just a wall jack somewhere. This is due to a protocol called DTP, the Dynamic Trunking Protocol. And there are several different modes that each switch port can be in. What we would have wanted that switch port to be in is when we do a switch mode access. So an access port is for like a printer, a workstation, a server, something that is only going to be communicating with a device. There's another mode that we can set up. And if you look at this switch here on the right, both of these should have the switch port mode trunk command turned on, switch port mode trunk. And what that does is it means that you're only going to be a trunk port. But there are negotiate modes. Negotiate modes are desirable or auto. And so let's go back to the previous switch. So if this port right here is in negotiate mode, let's say it's in dynamic auto, it's going to, if it finds a trunk port, then it's going to automatically turn into a trunk port. All right, so what if it's in dynamic desirable? So if both of these are in dynamic desirable and a cable is plugged into both of them, they want to be a trunk port, so they'll turn it into a trunk port. The reason why we have these different modes is because what we want to be able to do is create a situation where if one switch goes down, it'll automatically change the architecture so we don't lose anything. But what that also means is that if I'm an attacker, what I can do is I can set my switch to one of like a trunk, and if that is set up improperly, now I get all of the information for all of the VLANs sent to my hacker switch, and so that allows me to do a lot of extra work on that network. There's another one too called double tagging. So when you have, this is going to be an Ethernet frame, okay? I'm not going to, you have, your MAC address over here. On the end, you have a frame, check, sequence, and stuff like that. And there's space in here for a little tag that we can insert, and that is the VLAN tag. And what happens is when, let's go to this switch 2, and device is communicating on it, and when it leaves the switch upon egress, it gets tagged with the VLAN to which that communication is headed towards, that VLAN on the other switch. So what I can do though is there's still enough space that there's a software and tools that I can use to double tag it. So now I'm able to have an inner and outer tag, and I can get on 2 different VLANs. So that's actually a pretty cool tool that we can use to get more information than we should. All right, so there is yet another type of attack against switches, and that is called STP. Have you heard of STP? It's not that stuff that you put in your engine. This is a protocol that's built for switched architectures that have multiple paths through them. So these switched architectures are built, if you look at this one here, if you have a frame, it can go either this way or it can go that way, right? So we have 2 different paths that it can take. So STP will have as its, well, if you look at its definition, 802.1d is the original specification, but these days people use other specifications like PVSD Plus and RSTP, and there are others that are more complicated and less prone to issues, but if not protected, each of them can have this. So let's have a look at what can happen. So if you have a switched architecture that has multiple paths through the network, one of the things that's going to happen is there's going to be communication in between the switches. So switch 1 will communicate with switch 2, and they'll communicate with the root bridge, and they'll talk to each other, and they will form an architecture. So I'm going to go over to the board and talk about what happens when they put together this architecture. What will happen is there will be a switch that is going to be the root bridge, and it's going to be elected. There's an election that happens. And so the root bridge, by default, is going to have the lowest priority and MAC address. If all the priorities are the same, 32.769, 32.769, 32.769 over here, then what it's going to measure for the root bridge is the MAC address. So in this case, this MAC address was the lowest MAC address because all the priorities were the same. And so this becomes the root bridge. And when a switch becomes the root bridge, then the one with the highest priority / MAC address becomes undesignated, and we block communication going through that switch. Because otherwise, you could have this big storm of frames that go around this architecture and bring it down. So that's why you must block a port. So what this attacker did is they just got a switch with an extremely low MAC address, and now it becomes the root bridge, and all of the switch information goes through the attacker's switch. And bada boom, they took down the network. So there are several things that can happen for this. Number 1, it could cause a DDoS on the network. Number 2, it can cause loss of information on the network, as that attacker is now able to read data that flows through his switch rather than the original switch. Okay, so how do you defend against MAC spoofing? If you have a look at this slide, what we're going to do is we're going to do some of the same stuff we're talking about before. What we see here is we're starting with DHCP spoofing binding. We're moving into DAI, dynamic ARP inspection, but we have a new one that we see over here, which is IP source guard. And so we have a series of configurations that we'll run on a Cisco switch for different switches, Ubiquiti or whatever. There are different ways of doing this. But for defending against switch spoofing, we need to explicitly configure our ports. So for trunk, you do switch port mode trunk. For switch ports that connect to PCs and printers, switch port mode access. You want to make sure that you do that, and you make sure that you don't have negotiate. So you don't want it negotiating with another switch and then becoming a trunk. And then for double tagging, you want to defend your default VLAN. And there are ways to do that by, for instance, changing your native VLAN to a random number. But everybody that's in your network engineering team needs to know what that number is, like 9999. And then explicitly set the tagging to that native VLAN. Then there are other things that you can do, like for instance, remember I was telling you about how those switches communicate? They use bridge protocol data units, or BIPDUs, BPDUs. You can turn on BIPDU guard to make sure that all of these switches are talking only to the appropriate switches. You could do root guard to make sure that if you have a root bridge, that it stays the root bridge. We also have a loop guard to make sure that you don't allow those storms, those switching loops to occur. And then we have UDLD, which is unidirectional link detection. So with UDLD, it really helps to make sure that you are able to stabilize your Cisco protocol. And like I said, each bridge, each switch company has different ways of doing all of these. All right, let's talk about DNS poisoning techniques. With DNS poisoning, what we're doing is we can change the behavior of the network by altering the way DNS works. Essentially, what DNS is it is a way for a device to use an English name like www.microsoft.com and get a binary address and be able to take that browser or whatever to that address. So we have a couple of different poisoning techniques, or a few of them that we want to talk about. So if we look at the first bullet point over here, we have a DNS server, and it believes that it got an authentic update, but in reality, a hacker gave it the update. And so we give it the IP address to a rogue resource where perhaps a script can be run, and so we are able to poison it. Now, there's a really good tool for that called derp and spoof, and so let's look at that over this derp and spoof, and you can create a fake DNS entries and redirect that query to the wrong location. All right, so another item in DNS the hackers use is intranet or internet DNS spoofing. So in this case, it is intranet. So when you look at intra, that is on the LAN. And so let's follow the path. The first thing that needs to happen is this attacker is going to poison the router, redirecting internet requests to his machine. The next thing that happens is this student or user is going to an FQDN, www.xsecurity.com. And there is nothing listed in the cache. So what it's going to do is query the DNS server. But the DNS server is poisoned. So the DNS server is going to send back a response, but it's a poisoned response. So now when this guy goes to that location, they end up going to the fake website. All right, so now let's look at the next type of DNS spoofing, which is internet. So now we're not on the network, we're on the internet. So in this case, we have a machine, but this machine has been infected with a Trojan, and we have changed the DNS server address to the attacker. And so now when they try to go to a website, they get redirected to the attacker's fake website because they're using the wrong DNS server. And then we have proxy poisoning. So there's this area in your computer called LAN settings. And you can go to the LAN settings. You can do it through your browser or through your operating system. And in the LAN settings, you can get to proxy addressing information. I think on Windows, you can actually hit your Windows key and type in proxy, and it'll take you to those LAN settings. And if this IP address is an attacker IP address, then everything your browser does will go through the attacker's proxy, and they can control everything that you do. So that would be proxy server DNS poisoning. And then the next thing we look at is DNS cache poisoning. As we go through the rest of this class, you'll see there are all kinds of caches. We just talked about ARP cache, and now we have DNS cache. We'll see there's browser cache and many other stashes of information. So what happens in this case is we're going to alter or maybe add forged DNS records into the resolver cache. What is resolver cache? Well, let's talk about how DNS works. So in general, what's going to happen with DNS is a user is going to want to get to a resource. So the www.xsecurity.com. So they want to get to this resource. The first thing that it's going to do is it's going to go into the local DNS cache. It checks the DNS cache to see if that entry is in there. If it's not in there, then it will look at its list of DNS servers. Sometimes people have multiple DNS servers. This one you might be familiar. This one also might be familiar. 77, right? So these are DNS servers you can get on the internet. And so what it'll do is go to the first one that's on the list, and it'll query that DNS server. And it'll say, hey, DNS server, do you have this? If the DNS server has it in the DNS cache for that server, then, and the entry is still fresh, then it'll respond back right away with that cached entry. But if the DNS server does not have it in its cache, then what it's going to do is it's going to do a query. There are several different types of queries that it can do to go find that information. All right, so that's how it works overall. So let's look then at what happens in this case. So this guy queries DNS because it's not in his cache. The second thing that happens is it sends that query to a different DNS server that's authoritative for that zone. But what happened is the response is not sent back from that authoritative server because of these forged DNS records. And so the attacker sends back that forged response. The DNS cache of the user is now updated. So every time they go to the IP address for this site, it's going to always take them to the fake website as long as that record is renewed or not removed. So I just wanted to pause here and talk a little bit about how DNS works because that's pretty important for this class. All right, how do you defend against DNS spoofing? Well, the biggest thing that you want to do to defend against DNS spoofing is use DNSSEC. I mentioned this a little bit earlier. What DNS security or DNSSEC does is it binds that device to a specific DNS server so that it won't ever go out and reach out to a rogue DNS server. Let's look at the second one that we want to do. The second one we want to do is to use SSL. So remember talking about ubiquitous encryption? Well, there's some encryption. And then we want to do several adjustments like resolving all DNS queries to the local DNS server. Remember what I wrote on the board, 8.8.8.8? That is not a local DNS server. You don't want to put that on your workstations. You want to put the local DNS server on your workstation and then have the edge server do the queries and find the information. Configure your firewall to restrict external lookups. Do you also want to implement an intrusion detection or intrusion prevention system? Want to configure your resolver to use a new random source port for every outgoing query. Anything that can be predicted is hackable. Restrict DNS recursing service, full or partial, to only authorized users. Use NX domain. What this will do is if there is a non-existent domain, it'll drop the query. Also, secure your internal DNS servers. Make sure that you use static ARP and IP address. Let's talk about that just very quickly. So when you do a ARP query, it puts that information in the cache. Most computer systems that I have seen have a dynamic entry for the default gateway. So in other words, that device said, hello, I'm looking for the default gateway. And the default gateway said, hey, I'm the default gateway and here's my IP address. And then it ends up as a dynamic entry in the ARP cache. So what should happen is in a well-organized organization, you create an image for your workstations, for instance, and you put in a static entry to the default gateway so that an attacker can't spoof it. All right, let's look at some of the other ones here. We have static ARP and IP tables, where you talked about that. SSH, hey, more encryption. Do not allow outgoing traffic to use UDP port 53 as a default source port because people can spoof DNS servers otherwise. Audit your DNS server. You want to make sure that you're ingesting, processing, and looking at every single log that comes off all your servers, including your DNS servers. Sniffing tools. Let's have a look at some of the tools you can use for sniffing. All right, so if we look at this first one, what we see is Wireshark. Wireshark is amazing. It's a very cool tool. As you can see here, right here on the right is a TCP stream. So I select this frame, and normally this frame and the next one in the communication are mixed up maybe by hundreds or dozens or thousands of other frames. But if I select this frame and I tell it to do the TCP stream, I can watch the entire communication that's associated with that frame. That's very nice with Wireshark. But Wireshark goes beyond that too, because Wireshark has the ability to do filters, where we can filter IP address, filter port. We can filter against something with an exclamation mark and say, hey, don't give me that IP address or port or protocol. And we can do very sophisticated filters with Wireshark. So even if there are hundreds of thousands of entries that you've gathered with Wireshark, you'll be able to filter for just the ones that you need. The next thing we look at then in this next slide is CASPA, Portable Network Analyzer, and OmniPeak. Again, these are Wireshark-like. Their graphical user interface, they're a little bit more colorful than Wireshark with a little bit different features. We have the real-time threat analytics, and this one here, PTRG Network Monitor, pretty good. We also have Network Performance Monitor. So these are some pretty good tools to watch what's going on your network and be able to characterize that traffic, follow that traffic, and therefore find out if somebody is hacking your network. So you don't want people like me sniffing the network. Well, there's a way to take countermeasures against sniffing. Let's look at some of the countermeasures that you can do in this section. Okay, so for sniffing countermeasures, how to defend against sniffing. The first thing we want to do is restrict physical access. The reason we restrict physical access is because of what I was saying before. If you can touch it, you own it. And so somebody can just plug into that port, like in the conference room. They can plug into that port in the cubicle, in the wall, or whatever, right? Use end-to-end encryption. Make sure that you permanently add MAC addresses to the gateway and to the ARP cache. We talked about that a little bit earlier. Use static IP addresses and ARP tables. Turn off network identification broadcast if possible, so someone can't put a rogue device in there. Use IPv6 instead of IPv4. In fact, what you might want to do after we're finished with this module, just go back to your office and convert to IPv6. I mean, how hard can it be? Come on. Actually, IPv6 is one of the most difficult projects. We've been trying to convert to IPv6 since like 2000 something or other, 2003. So yeah, it's not that easy. Wish we could just do that. But also use encrypted sessions, SSH, etc. In fact, the most important item that you can do on your servers, on your workstations, in your browsers, with your apps, is to make sure that you are encrypting everything. In fact, if you encrypt it's very unlikely that somebody will be able to do hardly any sniffing on your system. So in fact, this module and the next module, encryption is one of the major keys to avoiding the activities of hackers like you and me. A few other things that you can do to avoid sniffing. Let's look at some of these. Oh, all of them that involve encryption would be like 12 encrypt wireless traffic, 8 HTTPS, 10 SFTPS, 11 SMIME, and SSH. So a lot of this is encrypting, right? Ubiquitous encrypting. Also, ubiquitous IAM. Down here we have ACLs, and we have ways of making sure that we know what traffic is on that system. Another thing we want to do is find out, detect if somebody is sniffing on the network. So remember, in order for a network card to be able to do sniffing, it has to be in promiscuous mode. We can detect that. Nmap is a good tool for that. We'll look at some others. You want to run an IDS to make sure that the MAC addresses of any of the machines, that it doesn't change, right? If someone changes their MAC address, then they might be running a sniffer. The next one is you can run network tools to constantly watch that network to make sure you characterize, analyze, normalize traffic. Let's talk about some of the behavior of sniffers. So a sniffer, when you send in the wrong MAC address, it will still respond. A sniffer, unlike a regular network card, it will do reverse lookups automatically. So if I do a ping and I give it the wrong MAC address and I get a response, hey, there's probably a sniffer there. If I send in a ping, DNS probably will do a reverse lookup. There might be a sniffer there. If I use ARP and I use the wrong MAC address and it responds, there might be a sniffer there. So it just behaves differently. And we can send these in manually to try to determine if there is a sniffer. But we have tools. I mentioned Nmap before, and that's my favorite tool for detecting and determining sniffers. And that is the script sniffer-detect. And then right here we have a specific IP address, .19. But you can do an entire range and just find out if there are any sniffers on that entire subnet. And then we also have a nice little tool over here called NetScan Tools Pro. Got a nice graphical user interface, many different capabilities. And one of those capabilities is to be able to detect sniffers. Okay, so that brings us to the end of the sniffing module. I'm a little bit sad about that. Not actually, I'm pretty happy. This is a good module. And we learned quite a lot about sniffing, especially the fact that it's not just some static thing you do collecting packets, but instead what we can do is we can dynamically interact with the network using things like ARP and other tools like ARP poisoning, MAC attacks, DHCP attacks. We can do snooping attacks and many others that we can do to go grab data from all over the network. And so it's very cool stuff that we can do, but sometimes it's just not enough because sometimes people do crazy things like encrypting all of their communications. How am I going to hack your network if everything is encrypted? So that is why we have the next module that we're going to go into, social engineering. If you can't hack your way into the network, just ask somebody. So we're going to do the lab, and then we're going to do some social engineering in the next module.